Welcome to the 7th drill. Today we're going to be talking about the intercept only model, as well as some stuff on effect sizes, power computations, and then at the end I'll touch a little bit on user-defined functions. I want to be absolutely clear that you will never ever have to use user-defined functions for Bill's class in particular, so it's not required for the course to know how to make these functions. But if you plan on being an R user and actually using this in your own research and in real analyses, then you'll find yourself often writing what I'll call helper functions, which are just like very specific, contextual specific functions that help you in a particular way, and so you just program something, because there's a saying, if you do something more than 3 times, write a function for it. And so when you find yourself in your own work repeating things over and over and over, being able to turn that into a quick function can really help you out a lot. We're going to be using the of course, tidyverse today, which I've already loaded it, which is why it didn't show up in the console down here. But then also LM support. We'll be using model effect sizes today, and then the PWR power library. If you haven't installed this, you'll need to install this either with install packages, or you can use the install packages box up there. Finally, for today, running options SciPin equals 10 again. I just wanted to make this explicit, that just know that you won't always have to put this in every script. In fact, I have this in far fewer scripts than I do. I have it in fewer scripts than I don't. So it's just by coincidence that this particular data set that we've been using gets those really tiny p-values, and so like forcing scientific notation. So I just don't want you thinking that, like, as you move forward, when we get into other data sets, that you always need to put option SciPin equals 10 in every script. Normally you don't put that in your script until you run into a place with scientific notation, and that's if you want to do that. But anyway, so we're going to be doing using the same data this week that we've used before, the bias data, looking at the exact same stuff, even the same models. So I left in here to explore your data with glimpse and describe. I'm not going to waste time on actually talking about them today. I put these in here just to try to reinforce the point that you should always explore your data whenever you pull data in, especially if it's new data. And then also, so we're looking at the change in IAT scores between week 8 and the baseline. So we create that IAT change variable, and then we create our we fit our one parameter model, our intercept only model, using the LM function, and we tell it IAT change regressed on the intercept. Remember that that's not regressed on 1, that 1 means the intercept, and then our data equals bias, and we're going to save that as a model called mod.int, which is my notation for the intercept only model. And then so now that we fit our model, we can look at the summary of our model. And so when we look at the summary of our model, what that tells us is that our estimate here, as a reminder, that the intercept is the mean of the outcome when everything is 0, or when everything else is 0. In this case, there is nothing else, so we know that that is just the mean of the outcome. So the mean IAT change is negative 0.24140, and our F is 49.37, and our P is less than 0.001. We get our degrees of freedom down here. Again, this intercept only model isn't the most intuitive thing to understand, because it's not particularly useful, and it's not something that we actually use a lot, but it's a logical first step for how this modeling process works. But so if we want to look at the confidence intervals of our parameter estimates, we can just put our model in confint, CONFINT. This function here will give us those 95% confidence intervals by default. And so some people wonder why it says 2.5 and 97.5, and that's because if you take 2.5% from one side and 2.5% from the other side, then total that is the 5%, and so that's 95% between 0.25 and 97.5. And so the confidence intervals for this estimate here. So our estimate is negative 0.24. Our confidence intervals are negative 0.3 to negative 0.17. And so, like, pulling straight from the chapter, it says that with our confidence intervals, that's where we're trying to get at the actual. We're trying to say we are 95% confident that the true population, mean there is within this range, within negative 0.3 to 0.17. A lot of people, I hear people mis-explaining what confidence intervals are a lot, and they'll say something to the effect of, well, if we did this experiment over and over and over and over and over again, then 95% of the time our mean would be between negative 0.3 and negative 0.17, and that's not what the confidence interval is. It is not that. It's not about the samples that we're drawing. It is about the population. We are saying we are 95% confident that the true population parameter is between 0.3 and 0.17. So again, the confidence interval is about your population, not about your samples. And so the way that you would report this, as far as how you write it out, would be, F1, 77, your numerator denominator degrees of freedom, equals 49.37, P is less than 0.001, and then 95% CI, and then in brackets your lower and upper bounds of that confidence interval. So a intercept-only general linear model is exactly mathematically equivalent to a one-sample t-test. So just to demonstrate this, again, we have, if we look at our model summary, and I'm also going to run a one-sample t-test and pull up these confidence intervals again. So here at the top, we have the intercept-only model, a regressing IAT change on the intercept. Here we have a t-test where we just put in a single column, so it's doing that one sample t-test, and we can see that our t-test is negative 7.02, and our t up here in our model is negative 7.02. Our degrees of freedom 77 and 77. Our p-values are the same. Our confidence interval here is the confidence interval for the t-test, which is the same as our confidence interval here on our model. And then finally, our t-test also reports the mean of x being the variable that we put in, which is IAT change. And so that mean lines up with our estimate here of what that intercept is. So again, with a lot of these linear models, there are equivalent tests that you'll hear, such as t-tests, ANOVAs, etc. And so in this case, an intercept-only model is the exact same thing as a one-sample t-test, where it's just comparing that the mean of some variable against 0 and finding, is that significantly different than 0. So again, that t-test and a one-parameter intercept-only model are exactly one and the same. So getting into effect sizes real quick. So just as a reminder that PRE, that proportion of reduction in error, which is partial eta squared, It's simple calculation. It's just the difference in error from your compact and your augmented model over the amount of error in your compact model. Or 1 minus the error of your augmented model over the error of your compact model, and this is just because it's a mathematical transformation of this. And so here, even though it looks different, I'm not doing anything that we haven't done before. I'm taking that bias data, and here in this first bit, I'm creating a variable using mutate, creating a variable called square error int for my intercept only model, and that is simply the outcome minus the mean of the outcome and squaring it. And then square error null is the outcome minus 0 and squaring that. So I'm doing the exact same thing that we've done the last 2 or 3 weeks. I'm just kind of combining it into one step. So there I'm just, instead of creating a different score and then, squaring it from there. And then I take that, I pipe it into summarize, and I get the sum of this column, my squared error intercept and squared error null columns. And so when I run all of those, I end up with this that gives me that sum of squared errors for my intercept only model and my sum of squared errors for my null model. And so I saved that. I stored that into an object called SSE. Now you can see it down here in my environment. So now I can just call SSE $int, which is what I named it here, which is my augmented model, the sum of squared errors for that augmented model, and the sum of squared errors for my null model, which I stored here. And so I can just call those up individually now. So now coming back to these formulas here for partial eta squared, we can see that that is, if we do the sum of squared errors for our null model minus the sum of squared errors for our intercept only model, and then divide that by the sum of squared errors for our null model, we get our PRE equals 0.391. If we do 1 minus the sum of squared errors of the intercept only model over the sum of squared errors for the null model, we get the same result. But then there is a function that we use, or we will use a lot, model effect sizes, that E and S are capitalized, but the M is not. And so we just put our model, mod.int, that model that we created, put that into model effect sizes, which, as a reminder, this model effect sizes is from the LM support library. And when we put in our model into model effect sizes, it will report the effect sizes for all of the different parameters in that model. In this case, we only have one parameter to report, which is the intercept, and it will tell us that our partial eta squared is 0.3907. So again, here we get that exact same thing, but this is just where we manually computed this value. But this is where that value comes from. Now there's also this dr squared, the delta r squared column. We're not worrying about that just yet. That will come into play very soon as we get into multiple parameters in the model beyond one. But for now, we'll just you don't need to worry about that. We're only worried about this partial eta squared, which is the same as PRE. And so that's how that's computed. It is just a function of the sum of squared errors for some compact model and some augmented model. So the next thing we'll talk about a little bit here is power. And so in this PWR package, if you look at the help file, you'll see that there are a bunch of different, it says power.2p.test, power.2p2n-test, power.ANOVA-test, etc. And so that's for two proportions with same sample sizes, two proportions with different sample sizes. So there are all these different types depending on what type of statistical test you're wanting to do. The one that we'll be using is Power F2 test. This is what you use for power calculations for the general linear model, which is what we're using. So if we click on that and look at what the arguments are, we can see that it has this. Well, I have it over here, so we'll just collapse that down. Here's what it looks like, where we have U, V, F2, sig level, and power. And you'll notice, looking over here, that everything is null by default except sig level is 0.05. So what that tells you is that you can leave out the sig level argument, and it will always use 0.05 unless you tell it something different. And everything else is null by default. So the way that this works is where U is your degrees of freedom for your numerator, V is the degrees of freedom for your denominator, F2 is the F squared effect size, and then the power is the power level that we're looking for. So the way that it works is you have to enter in 3 of these 4 null parameters or arguments, and it will return whichever one you leave off. So if you're trying to figure out power, you leave that off. You enter your degrees of freedom numerator, degrees of freedom denominator, effect size, and significance level, and it will give you the power. If you put in V, F2, and power, it will give you U, etc. So you just have to leave off whatever it is that you're looking for, and that's what it'll give you. So here I put a few notes, and I put a lot of notes into this particular script, and the reason for that is of all the emails I get from other graduate students or faculty reaching out to me with statistics questions, probably 90% of the time it's something involving power, and I know that this was week 15 of the 2018 course because I constantly go back to that script to reference all this material, because I know that the power package doesn't necessarily have the best documentation. So I put a lot of notes in this, and so if there's any scripts from this semester that you definitely need to make sure you know where it is or what is in it, this would be one that is referenced back to a lot. So I put in a lot more notes than I normally do for that reason. So here I just copied and pasted this from our previous scripts, where, like, as a reminder that the degrees of freedom numerator is just the difference in the number of parameters in the augmented versus the compact model. How many additional parameters are there? And then for our degrees of freedom in the denominator, that's a function of the augmented number of parameters in the augmented model and our sample size. So again, that our numerator, that U, is the number of parameters in your augmented model minus the number of parameters in your compact model. It's oftentimes just 1 is your degrees of freedom for your numerator. Not always, but often. And then V will be your sample size, N, minus the number of parameters in your augmented model. So then also, that means that V, our degrees of freedom for the denominator, is our sample size minus 1 minus the degrees of freedom for the numerator. So V equals N minus U minus 1, and because math, N equals V plus U plus 1. Why that's relevant, we'll see here shortly in an example. One way to compute F squared, the one that we're going to use today, is computing it based on PRE. And F squared is just PRE divided by 1 minus PRE. But there are multiple ways to compute F squared depending on what information you have. As we get into multiple parameter models, we'll start talking about the idea of a focal parameter. And so, when we start looking at R squared as our effect size, that we'll have an overall R squared for the model, known as model R squared, and then we'll have the delta R squared for one of the parameters, our focal parameter. And so there is a way to compute F squared based on the focal parameter and the model R squared. And so I'm just trying to plant the seed to say, hey, there are lots of different ways to compute f squared. It may be that you already have an effect size. You have, Cohen's d computed, and so you just need to look up an effect size converter and say, well, how do I convert Cohen's d to to f squared, or how do I convert Hedges g to f squared? Whatever you have to convert that to f squared. So, but today what we have is PRE, so we're going to be using PRE over 1 minus PRE. And then I just threw in here like these rules of thumb for f squared, that 0.02 is small, 0.15 is medium, and 0.35 is large. Again, those are just very fast and loose. It varies widely by field, so don't take that as the biblical truth. So the first type of power analysis we'll talk about, and it makes me want to throw up in my mouth a little bit, is post hoc power. So given some sample size, some effect size, and some alpha level, and thus the DF and the design with a numerator, compute power. So after we've run a study, we want to see, how much power did that study have, and for reasons that Bill may or may not get into. A lot of statisticians will tell you that post hoc power computations are completely pointless. That it is literally just a transformation of the p-value, which presumably you've already reported, and so it's completely redundant. And I am one of those. Like, I've gone as far as to tell a reviewer as much, and I just absolutely flat out refused when the reviewer wanted me to do a post hoc power analysis. I refused to do it. Instead, I added a footnote citing basically something saying that I reported confidence intervals for everything, including my effect sizes, yada yada yada, and so post hoc power analysis don't offer anything additional, and I've just flat out refused to even entertain a reviewer who wanted me to put this in a manuscript that I published. And then also Chapter 4 notes that confidence intervals are useful for describing post hoc the actual statistical power achieved in terms of the precision and parameter estimates. Wide confidence intervals represent low statistical power, and narrow confidence intervals represent high statistical power. So that's just it. Like, if you have crazy wide confidence intervals, then you can infer that it's meaningless. If I'm looking at something in my 95% confidence interval, say on age is between 18 and 78 years old, like, that doesn't really tell me. It's like, oh, so basically any adult age. That doesn't really refine it into like a specific time period of somebody's life that X, Y, or Z happens. It's any time that they're an adult. So that wide confidence interval doesn't give me a lot of confidence in like knowing that knowing somebody's age is helpful to me. But if you do feel compelled to satisfy the reviewers, here's how a post hoc power analysis would be done. So looking back at our model, we have our degrees of freedom. Our numerator is just the 1 because it's how many more parameters are in the augmented model than the compact model. Our augmented model has the intercept only. Our compact model is the null model with 0 parameters. So our degrees of freedom for the numerator is 1. For our denominator, our degrees of freedom was 77. For f squared, if we do PRE over 1 minus PRE from model effect sizes, we got that our eta squared was 0.3907. So if we run this line, we just store that f squared as mod.int.f2. And also just make a note, 0.64. Large was 0.35, and small is like 0.02. So this is ginormous. So our significance level, we'll leave at 0.5, and our power is what we're leaving out because that's what we're trying to compute. How much power was there for this model? And so we would put in those arguments. U equals 1, V equals 77, F2 equals mod.int.f2, which is this that we did. Then we leave our power as null, or you can leave this off. So these two, this line and this line, are identical. That you can just leave off the power if you want to. And so when you run that, it will tell you that the power, it computes the power at 99.9999998. So this post hoc power analysis shows that the power is 99.9, and you know, if that seems stupidly high and like nonsense, it's because it mostly is. And Bill's kind of talked a little bit about intercept only models not really being things that we work with because they aren't particularly useful and meaningful, at least not in our field. And like I mentioned, that's a ginormous effect size. But of course, you know, a mean only model has a huge finger quote effect of reducing the error beyond just predicting 0 for everything. So it's not necessarily meaningful. But here's the real takeaway that I really want you to bring out of this whole thing about post hoc power. If p is less than 0.00 or less than 0.05, post hoc power will mathematically necessarily always be over 80% at alpha equals 0.05. This is why, because power is a literal, post hoc power is a literal transformation of your p-value. So if your p is less than 0.05, you will always be able to say like, oh, well, we had 80% power based on post hoc power computations. And so it's pointless, and it doesn't add anything. And if none of you ever do a post hoc power analysis, that would make me really happy. So then, just to show you real quick, same thing. If we're just looking at how much power, let's say that same with the bias data. If instead our effect size would have been the cutoff here for a small effect size, then you know, our power would have only been 23.67%, and if it was a medium-sized effect, power, you know, a post hoc power would have shown 92.49%. So then a priori power. Now this is the actual useful power. This is the one that you should know and you should be using, because you should be thinking about power on the front end of your studies to make sure that the studies that you're designing, you have enough participants for the specific analyses that you want to do. So for this, you're trying to compute the sample size, the n, for a given power, effect size, and alpha, and DF numerator based on the design of the analysis that you're wanting to do. So in this one, we're wanting to see how big of a sample size we need. So let's say that we have this study, and we're going to ask participants how much money they would want to give to some charity, but to see if this amount, we want to see if this amount differs depending on whether we lead them to believe that we're actually going to get money from them, or if we're like explicitly asking them, hypothetically, how much would you give to this charity? So our model has two parameters that we're estimating, because we're estimating like some effect of the intercept and an effect, or we're estimating the intercept plus some effect of this real versus hypothetical distinction that we're making. And our compact model is only going to have one parameter because it's the intercept only, and we're taking out that real versus hypothetical parameter. So our u, our degrees of freedom for the numerator, is 1. V, that's what we're going to leave blank because we're trying to figure that out. We're trying to figure out our sample size. N is part of V, so we leave our V as null. For our F squared, prior research has shown that the effect on charitable behavior of real versus hypothetical processing, research has found PRE equal to 0.13, which is totally made up. I just made that up. But that's what we're going to go with. We're going to say that, hey, we have reason to believe, to expect an effect size, a PRE of, or eta squared, of 0.13. So our F squared is going to be 0.13 divided by 1 minus 0.13, or F squared of 0.149. Our significance level is going to be 0.5, and as the standard default, we're going to go with 80% power. So we put all that stuff in. We tell it u equals 1. Our F squared equals 0.13 over 1 minus 0.13, or we could copy and paste in 0.41494253, and we tell it that our power, we want 0.8, 80% power. And this will tell us our V, what we left off, is 52.5. Now, because N is part of V, recall that N is V plus U plus 1. So 52.5 plus 1 is 54.5, but we can't have half a participant, so we need 55 participants in this study that we've designed to have 80% power based on expected effect size eta squared of 0.13. We need 55 participants. But then there's another type of analysis that's the other one that is maybe something that you run into. And this is called a sensitivity analysis, or some may call this the minimally detectable effect size. And so the question here is if you give a sample size, a power, alpha, and the degrees of freedom numerator, it will return an effect size. And what this question is asking is, given this power, this this design, this alpha, and this sample size, what is the smallest effect that we can realistically investigate with 80% power? How small can the effect be before we don't have enough power to investigate it anyway? So here, let's just say we wanted to up the ante on our research. And so we wanted to make the real condition really real. So we were going to give them $5 and then ask them how much of that $5 they wanted to give back to give to charity. And then at the end say, well, actually, we need you to give all that back. We were just joking and you can't actually keep the money. But the IRB says, oh, you can't do that. Like, once you tell them you're going to pay them, then you have to pay them. But even more, it's apparently unfair to the people in the other condition that we were still just going to ask them hypothetically, how much would you give? The IRB says, well, you can't pay one condition and not pay the other, so you have to pay everybody. And if you don't do that, then you don't meet our ethical muster. But alas, we're poor grad students, and I have $200 to spend on this study total. So that means I can only run 40 participants in my study. So now the question is, what is the smallest effect size I can realistically investigate with 80% power using only 40 participants given this design? So again, our degrees of freedom numerator is 1. Our V is our N, which is 40, minus the degrees of freedom numerator, which is 1, minus 1, or 40 minus 1 minus 1, for V equals 38. We're going to leave F squared, or F2, blank. And then our power we set to 0.8. And we see that F equals 0.2066. To convert F squared back to PRE, or partial squared, the formula is, since F squared is PRE divided by 1 minus PRE, then if you flip that around, PRE equals F squared divided by F squared plus 1. So if we take that F squared and plug it into this formula, we get our PRE equals 0.17. So PRE of 0.17 is the smallest effect size we'd be able to actually investigate with only 40 participants, given the way that I've designed this study. So in other words, if we ran this study and the effect size that we actually found in our study was 0.14, then we can't really say that we got much out of this study, because based on our sample size, we can't detect an effect size less than 0.17 with 80% power. We're going to be underpowered to assess any effect sizes smaller than that, I guess is how you could put that. So whenever your study is designed with constraints on the sample size, you may use a sensitivity analysis on the back end to see if the effect size that you found is one that you can actually investigate with enough power. So then the last thing here that I'm going to talk about real briefly is these user-defined functions. And like I said, you can cut it off here if you are not planning on using R once you get out of this class. If you are, then stick around for another minute or two, because being able to write your own functions really does make life a lot easier for you in a lot of ways. So the basic way that it works is that you type in like function, and then in parentheses some input or inputs, and then in brackets next to that you put the things to do with those inputs, and then you use your assignment arrow to store that as some name. And then once you do that, you then have a function that has then like whatever you named it here, and you can use that like a regular function. And so here, for instance, if I'm wanting to convert my PRE to an F squared, let's just say up here, instead of typing all this out like this, that I want a function to convert that PRE to F squared for me. So here I just say function and then PRE, and so I'm only asking it, this function only takes one input, and then it takes that input and it does that input divided by 1 minus that input, and that's what it returns. So when I run this line, and I store that as a function called f2 underscore from underscore PRE, and down here in my environment you can see I actually have these functions, and I now have this function. And so if I start to type in f2 underscore, you can see that it has f2 from PRE, and then in fact right here when you hover, and I mentioned this here also, and this is what I mean, that if you click and hover and wait for this little box to pop up, you'll see that it asks for the input that it's looking for is PRE. It's asking for what I put in here and what I specify here. So the way that this works now is if I take what I had before and I take that, instead of saying 0.13 divided by 1 minus 0.13, I just use my f2 from PRE function and tell it that my PRE is 0.13, and now when I run this function, it does that computation for me. So I can now just plug that function into my power f2 test and get the same answer that I got before. Now the reason that this is useful is because like this, and this in particular is not a very useful function. But sometimes you'll have multiple inputs, and so in that case, doing this just like before, and pay no attention really to the spacing of this, because you could delete all this where it is all in one line just like up here, and you have function, and then this time I have two inputs, something called this dot thing and something called that dot thing. And then inside the brackets, I put what to do with those inputs. So I want to take this dot thing and add it to that dot thing. And I store that function as a function called unnecessary addition function. So if I run that, we can see now down here in my environment, I once again have this other function. And again, if I hover over it, you can see here with like this little function help pop-up box, whatever you want to call it, it will tell you whatever you name the inputs when you define the function, it asks for this dot thing and that dot thing. And now if I put these in, what it does is the first thing that gets put in becomes this dot thing. So that 3 becomes this thing, and this 4 becomes that thing. And then the function adds together this thing and that thing, such that now if I run this function, it will return 7, because it takes this thing and that thing and adds them together. And so earlier I mentioned briefly that as we start getting into multi-parameter models, when it comes to power, we may be looking at things like focal parameters and model R squared and a few other things. And so in particular, when you're doing power analyses, you may be toying with two separate things, and so there may be something that you put here, and then once again you have two separate values that you put in here for whatever. and for those reasons, these little helper functions can be a lot easier for you rather than having to retype a bunch of different stuff over and over and over. And so that I'm gonna wrap it up right there. If you have any questions, let me know, and if not, then I will see you all on Thursday or Friday.